So as I said before here, this peak is important. When you see a big peak here at the utmost right of the plot, it points to contamination. How can you check the contamination? Well, for that, you go here to the overrepresented sequences table. So to generate this table, FASTQC takes every read that makes up more than 0.1% of your FASTQ file and blasts it against a database of known contaminants. So for each of these reads, you see the sequence, you see how many times it occurs in the FASTQ file, and you see which percentage of the FASTQ file it makes up. So this first read here makes up 13% of the FASTQ file. And then the last column contains the results of the blast. What is he blasting to? Well, typically known contaminants are adapter sequences. So during the library prep, there is a step where you are going to ligate adapters to the fragments in the library, but of course ligation is a process that you cannot control. So adapters will also ligate to each other, forming these adapter dimers. These adapter dimers will be in the library and they will be sequenced along with all the fragments in the library. So, and this is why he is blasting against a database of known adapter sequences. You can check the documentation of FASTQC to see which adapters are in the database. You have a list here. If you don't see the adapters that you have used during library prep, you can create a FASTA file yourself with the adapter sequences that you have used and give it to FASTQC as the database to use for the blast. So most highly duplicated reads will be adapter dimers, but there are other sources of contamination in next-gen sequencing libraries that can pop up in this table of overrepresented sequences, because you see that there are also reads here that do not have a hit during the blast. So many of them that do not have a hit will be adapter sequences with sequencing errors, because the blast is quite strict. It doesn't allow for many mismatches. But some of these sequences can also originate from other sources of contamination. For instance, sequences from VIX virus are often used by sequence providers as a sort of a control. So they are added to libraries from organisms with extreme GC content like Arabidopsis, Plasmodium bacteria, or small libraries that contain a very limited set of fragments. Why are they used? Well, because during the first 10 cycles of the sequencing, the sequencer still has to do calibration. And for this calibration, it's very important that he can calibrate on sequences that have a random distribution of A, C, G, and T. However, if the organism that you work with has a very extreme GC content, there will not be a random distribution of A, C, G, and T, but you will have much more G's and C's than A's and T's, or vice versa. In that case, the sequence provider will add these sequences to make the distribution of A, C, G, and T more random. And the same is true for these libraries. If a library only consists of a few fragments that have been amplified a lot of times by PCR, then also here you will not have a random distribution of A, C, G, and T. In DNA-seq libraries, you can also have repeats popping up as overrepresented sequences. And in RNA-seq libraries, you have the highly expressed genes, of course, and also the ribosomal RNA contamination. So the best thing that you can do, if you see these no hits and you don't know where they come from, is simply to take these sequences and blast them yourself. You blast them to the organism that you work with to see if they might be repeat sequences or ribosomal RNA sequences or highly expressed genes. And you can blast them against the FASTQC virus sequence to see if they come from here.